All right, so it's
This on.
ready to go? Okay. All right, well, thank you, and thank the organizers for letting me talk to you today. My name is Richard Sharp, and I have been involved in, I guess I'd say, the data science field around the Seattle area for the last several years. And I hope to highlight how I think a mathematician working in data science is why I think it's worth it, because it's much more typical to find not a mathematician, but someone with a computer science background working in this field. Although I have to, very honestly, admit the distinction between mathematician and computer scientist in many of these cases is very, very thin. Yeah, is this working? Yeah. Is it turned on? All right. Does that work? Is that picking it up a little bit better? All right, I'll just try and raise my voice. I have become unused to speaking in front of an audience lately. I've been, I haven't been teaching less than I used to, I guess I have to admit. So I was saying it's much more common to find a computer scientist in a data science role. The distinction between a computer scientist and a mathematician can be very thin or non-existent, but nevertheless, I think bringing a mathematical background, much like my background has many of those valued skills you put up there, and I think that has value in data science as well, and I hope to highlight that a bit. So first, a little bit about me, and then a little bit about the time I've spent at two companies out in the Seattle area, one of which you've probably heard of, and the other of which you almost certainly have not. So background, I got a PhD in 2005 from Princeton, working on numerical multiscale methods. So all that numerical analysis, optimization, linear algebra were components of these things. I went on to do a couple of postdocs after that, discontinuous Galerkin methods to simulate electron flow, mesoscopic modeling of materials. And so a lot of traditional activities for a numerical analyst with a touch of computing in there. And that brought me up to about 4 years ago when I moved to Microsoft. I moved to Seattle and I got a job in Microsoft. That's a big jump, but it was really a solution to a two-body problem. I got there because my wife was there and we wanted to be in the same place. I narrowed my job search significantly to one geographic location. But nevertheless, I've been very happy with the result in the corresponding time. So I initially joined Microsoft. I joined a product group, not Microsoft Research. So Microsoft does have a large research organization. There are a lot of really wonderful people there. There's at least one Fields medalist, in fact. Probably only one Fields medalist, but nevertheless, the point is they've got good mathematics there. But that's not what I did. I joined a product group. I joined a group that's goal is not to produce papers, but to produce software. And initially, that was an automatically scalable math library called Cloud Numerics. The idea being you sit down and write a matrix equation when you're writing code. You write something like x is equal to a over b in the matrix sense. And you don't have to worry beyond that how big that matrix is and whether it fits in memory, or these good things will take care of that for you under the hood. Another thing that was interesting there, I was not the only mathematician when I showed up. And in fact, there is a SIAM report on STEM careers. There's a Korean translation of it here. One of my very close colleagues is profiled in that. Mary Beth Frybar is profiled in that pamphlet there, and she was somebody that I met on practically my first day and worked closely with during my time there. She's an optimization expert. So there are opportunities and recognition that mathematics is a valuable tool beyond MSR at Microsoft, which was something I found interesting. It's a bit rare. It is a large company and there aren't that many of them, but there is a place for it. And eventually this work led to the data science, traditional components of data science, notably machine learning, and a product that was recently announced called Azure ML. So what did I work on when I was there? I worked on a product called Azure ML. It's a cloud service for experimentation and deployment of predictive models. So we've heard a bit about predictive modeling here before, and the problem is not only to find a good model, but often find a good model, connect it to your data, which can be a real mess, and not just do the mathematical search for here's a good model that makes a good prediction, but put that thing up in production. Get that thing running every day, making those productions, and we heard yesterday a lot about control systems, essentially controlling, in this case, one example here from CMU, controlling aspects of building operation, such as temperature. So there's an example here where Carnegie Mellon has built a solution that has an Azure ML model at the heart of it. They've connected a bunch of building sensors from across campus to Azure. So if I haven't explained it, Azure is Microsoft's cloud offering. So it's a blanket term for everything cloud computing at Microsoft, a lot like AWS at Amazon is Amazon Web Services, their main cloud offering. What it means is I can plug all these sensors into more or less the internet, and off this data goes into Microsoft's data centers. That data gets picked up there by a model, which is composed visually like this. The programming paradigm for building models in Azure ML is to drag and drop these little modules here. You can't quite read what's on these things perhaps, but each one of these modules is some sort of algorithm or data cleansing step, etc. And there are inputs and outputs and data flows all over this thing. The heart of it is something like this. Here is a machine learning model being trained right there, data coming in from one side, model specification coming in from another, and a resulting model coming out the other end. You can compose these things visually, which is great for people who don't want to be down deep in say C#, which is a programming language that you'd have to get used to if you wanted to build such a thing on Azure by yourself. And after you're done, you can launch this thing into a production setting. So they've built a couple of models, one for predicting solar radiation on the outside of a building, which helps as part of a building temperature control problem, and one for predicting faults in hidden components. So hidden as in there is some sort of mechanical component inside the wall of the building where you can't just walk up to and visually inspect it, but you do have some data coming off of it, and you would like to know, is this thing working properly, preferably without tearing down the wall first. So that's one application there. Okay, so what was I doing there that was making use, what was valuable, what was mathematically valuable there when I was there? Or what do I want to say here? Not what did I get to do when I ran off to my office and hid by myself and played with this thing? That was fun. But what was I really providing as a mathematician to the large organization here? One of the most valuable things was I was translating between the mathematics, meaning the heart of those modules there. I was translating for the engineers that were building this. I was translating for the customers who were using this. Engineers were asking questions such as, which modules do we need, and how do they need to interact in order to build successful models like this? What algorithms do we need? How do they need to behave? One of the more interesting things that came up, I wasn't expecting this, but machine learning algorithms are essentially random. So imagine something like k-means clustering is a good example. It's an iterative method, and step number one is often to pick a random initial condition. Well, that means the same input generates different outputs every time. That's not something that a computer scientist, a CS tester, is used to. Same input leads to the same output, and the traditional way of testing many things is to look for, you repeatedly put in inputs, and you repeatedly expect bitwise, bit by bit, the output to be the same. So teaching them that, no, the output of this algorithm can be different every time, but here's how you make sure that it's reasonable was an interesting part of the job. And then for customers don't come with, we heard this a couple times yesterday, customers don't come and say, I have this math problem, here's how I should specify it. They come and say, I've got this problem, I want to make this process better. How can we do that? So translating that into a mathematical framework, well, what framework? This framework. Translating that into a problem that could be solved with the modules that we had was another interesting part of the job. So that's where I think being a mathematician was something a bit unique and valuable for Microsoft. What did I learn? The other interesting thing about this was that I got to learn some very interesting things. We definitely heard of this yesterday, the importance of software engineering. That is not something I appreciated at all until I moved there. This is a service. It has to run every day. It has to run for many, many, many people simultaneously. It can't fail. If it's down, we're not making money. So the reality of what has to happen in order to get this thing up, make it robust, make it scale, keep it secure. Microsoft is this is Microsoft's computing power that you are using. Microsoft is a favorite target for abuse. So if you don't worry about things like security and et cetera, someone is going to spin up millions of, well, thousands or hundreds of thousands of computers and just have them waste time for you. You need to worry about an awful lot of things that are not mathematics, and that means you need good software engineers and you need a good team around this to build something that can be reliable in the real world. Other interesting things. So the dynamical nature of data was something I came to appreciate a bit more, meaning I think I felt too much before I started this that a snapshot of data, that was the data. That's how it was. That's how it lived. I appreciate it a bit more now that the data is always changing under your feet. If I were to take a sample of data right now, measure some property of it, and make a conclusion, I have to realize that that sample is something from the past, that new data has come into the system since I looked at it, and that the reality of how things are operating now may be different than they were before. Another very interesting thing I got tied up in was temporal queries. So asking questions like, what is the mean of the data? Took on a new meaning to me because it became apparent pretty quickly that it's really important to specify over what time period. And that if you were to say, what is the mean of the data, and start writing an algorithm that says, first, sum all the data, you've already failed. You've fallen into the trap of imagining that you have all the data in a world where this is a service. Data is always coming in. Data is, for practical purposes, infinite. It has no end. It will always enter. So you have to take care to work over, to define your sample. Often that means over what time period. All right, so moving on. I did that for a few years. And earlier this year, I moved from a company of 100,000 people to one with 100 people in it. So that's I think a little bit of a difference now versus some of the other stories we've heard earlier. And I've got to say, I don't know how common it is for smaller companies like this to hire a mathematician. Certainly, the idea of a startup in Silicon Valley with just a handful of people sitting in a garage working on a product, the first person you hire is a software engineer because they've got to do all that software engineering I spoke about. It'd be nice to have a mathematician early on, but if you don't have a web page and you don't have a public presence, then you've got no product. So it's not necessarily the first hire. Nevertheless, there are good math jobs at small companies like this. What we do is contextual marketing for telecoms. I'll talk a little bit more about this. We're headquartered in Seattle, and although the contextual marketing part of the business is relatively new, the company has been processing telecom data for the last 15 years. One thing that they've gotten very good at is ingesting call records and things like that from on a large scale and managing that data. So, what are we doing there? Boils down to there are millions of people in a cell phone carrier's network. We work for that cell phone carrier. And what we want to do is present them with some sort of offer, say a text, a package of several, for texting data, a package for voice minutes, etc., at the appropriate time, to the appropriate person, etc. And at heart, there's some fairly interesting pieces of mathematics creating the models that do this. So this is based mainly on the idea of nudges. So a signal, written, verbal, visual, environmental, contextual, the signal that's environmental or contextual that impacts an individual's behavior. I put this up here mainly because what we're doing now is social science at scale. I think we've heard a lot of the other examples we've heard up to this point. Not all, but a lot of them have focused on the physical sciences. But this corner of data science is really something I would point to as on the social science end of the spectrum. But I say at scale because we work with data that's coming in from 10 to the 6, 10 to the 7 people per carrier at once. So it's a much more fine-grained view of people's behavior than you could possibly have imagined, say, a decade ago. Well, maybe more than just that. And, we heard a little bit from Bell Labs, and I know that AT&T has had some good history here around some of these problems. So a little bit more about nudges. Here's an example of one. When I go every year to renew my car tabs in Washington State, along with plugging in all this data about the car, there's a little default down here. Yes, I want to donate $5 to Washington State Parks. That is the default setting. That is a nudge. It is a subtle way of getting you to go ahead and affect a behavior that you might not otherwise undertake. First of all, if you do happen to notice that this is set here and you say, oh, I would not have entered $5, but I feel bad emptying that field because I love my parks, then that's an example of how this can work. That's one simple example at scale with the telecom data, and I see I'm going to have to compress a little bit here. At scale with the telecom data, this takes the form of here's a text message. If you add more money to your account by the end of next week, we will give you some benefit in return. And the idea is really to drive you. So something like this, maybe this is the amount of money in your, let me mention quickly, and in fact this probably makes a lot of sense in this audience, wouldn't make as much sense at home. Most of what we're interested in is the prepaid market. In the US, people have 2-year contracts. They don't typically look at their bill. They don't typically have an idea about the balance of money in their account. In the prepaid market, you can use your phone so long as there is money in your account. So as your account balance dwindles, you periodically add more to that so they continue to use the phone. We don't want you to necessarily do this once sooner. We want you to do this more frequently. We want to nudge individuals in ways that cause their behavior to raise some broad performance metrics. So average revenue that you're getting from a customer, or reduce the amount of people who leave churn out of your network. These are the kind of goals that we have. So what's interesting for a mathematician here? Well, there's a good dynamics question. What are people going to do next? Look at all this nice time series data I have here. What's interesting for a mathematician? Well, there's a nice big graph to play with. 10 to the 6, 10 to the 7 people talking to each other. Just finally to kind of wrap up here, what has been useful? What have we done and what's been useful here? Well, one thing that has been very successful at Globys is that we have a science team, we have an engineering team, and we have a marketing team. These teams work together very closely, physically closely. I turn around in my chair and I can talk to the chief engineer. I turn to my right and I'm talking to the rest of the science team. The marketing guys are 2 desks over. The science team is composed mostly of PhDs from a variety of backgrounds, math, physics, computer vision, finance, etc. Our job is to deliver the predictive models, to automate the modeling process. I say automate there, but maybe thinking of things like adaptive numerical methods is a good way of sensing what I mean by automate. And we debug the math. I think we heard about this at, from in the Boeing talk in the morning yesterday. When something, the software engineers will tell you if numbers are coming in and numbers are coming out. We will tell you why the numbers coming out are wrong. We will try and discover, what is it about the properties of the numbers themselves that is wrong. And say, so the big benefit here is the company has a good, has a culture of valuing mathematicians and the science team. We're closely engaged with the engineering team, and I'll even toss in that we have had PhD candidate interns before that have done some fairly nice work, and we've gone as far as we even have some academic collaborations with other universities. I'll leave it at that.
Any questions for Richard?